Hello, people. Mm, 23.
Morning.
Morning. Where are you? It's 3:30. Hi, Serena and friend.
The phone. It's Adia.
Oh, okay. Adia Bagul.
Yep.
Okay. Wow, we don't have a lot of people today. We're at 24. Let's wait a little bit.
I know, right?
Sean Reeser just got up. It's morning for him. That's okay. Won't hold it against you. Can't miss this class. I know you learn so much. It's so intense. Hello, Saksham Luthra. Where are we at? We are at 26 participants. That's 25 students, about half. Let's wait a little bit because this lecture is going to be a little short as usual. It's a lot longer when I'm waving my hands and yelling at people. So it's no hurry starting. We're up to 28. What are we learning today, Stefan? Today is brain structure day. Nerves and where they connect, and then the brain structure. Do about half of it today and the rest on Thursday.
You mean Wednesday?
Yes, Wednesday. One day blends into the next. I've got classes on Monday, Wednesday, and Tuesday, Thursday, and I always confuse what day it is. How's the grading going? It has not begun yet. I've been just deluged with work lately, but I'm hoping to get them done in the next week. I hope. Sorry, everyone. Okay. Excuse me. All right, so let's go ahead and get started here. And maybe if we end early, I can get some grading done. Let's share my PowerPoint. Share my PowerPoint. Okay, so here we are taking a brain apart and looking at the pieces and then hopefully putting them back together. That's what it takes to be a doctor, you know. You can't just take things apart. Gotta put them back together. Okay, so why are we studying this? I'm just organizing my workspace here so I can talk to you more efficiently. Okay, so I can't see my chat screen when I'm in share a lot of the time. So I'm going to appoint someone. Today I will appoint Christy Trask. I can see your face. So if there's something that comes up on chat, can you tell me about it, Christy?
Yep.
I'm going to put you in charge of keeping my head in the game. Okay, so in general, each drug is designed to interact with the receptor for a specific endogenous receptor. So we kind of went through this exercise at the end of chapter 3, where you note that any protein in the cell could be a target for a drug. So a drug is going to be interacting with and mucking up some natural process going on in the head. And these receptors are in different places in the brain, and they're besides your ionotropic receptors, not just like spread all over the brain, but they're in specific areas with specific functions, which is good to us because that makes it easier to understand where the drugs are working and why they're working and what they're doing. And we'll see there's a lot of, like movement around the brain. I said this before. There's a whole lot of white matter in your brain. Did I say this before? I don't know. Your brain's got a lot of white matter, and that's all myelinated neurons, and those are called tracts. So we'll talk about different tracts in the brain and how they take information to different parts of the brain. Okay, so the nervous system is divided into two different parts. You've got your central nervous system, which is basically everything from inside your spinal cord and up. And then your peripheral nervous system, which is outside of your central nervous system. So you've got nerves that come into the dorsal root of your spine. That's the back of your spine. That's incoming information that then comes into the central nervous system and up the spine to your brain. And then you've got your ventral root, which is like information coming down your spine and going out into your body from there. In terms of your peripheral nervous system, you've got two different types of neurons. You've got your sensory neurons, which are going to come in again through the dorsal root of the spine and relay up to the brain. You've got two different kinds of sensory neurons. You've got internal and external. So your external are usually what we think about in terms of senses, your hearing, sight, smell, all of those things, but also touch and temperature of the outside of your outside body, and and all kinds of external information coming in. But you also have internal sensors, things like body position. You know, if your eyes are closed, you still know where your body is and where all your body parts are, because you've got internal proprioceptors that are telling you, constantly giving you information as to your body position. And that'll be really important shortly when we talk about your cerebellum and organizing smooth movements and stuff. Your body's always giving information to your brain about your body position, in terms of balance and where all your limbs are and stuff. And then other internal things are like oxygen amount, carbon dioxide amount, temperature, I think weight regulation, you know, how much is in your stomach, how much is in your intestine. All kinds of internal sensors are sending information back to your brain for calculations up there about what should be done. So that's the sensory nerves bringing information into the brain. Then you've got your motor neurons that are taking information out of the brain. So sensory information comes out, the brain decides what it needs to do. Brain decides what it needs to do to alter your body in some way. Then it sends information back down through the motor nerves. And the motor nerves, you've got two different types. One is usually what we think about, which is your somatic nerves, your voluntary movement. So your brain tells your hand to move somewhere. But then you also have the autonomic nerves, which are housekeeping, basically. Respiration, blood pressure, heart rate, digestion, all the stuff that keeps your body going. You don't really have to think about it. That's the autonomic nervous system. And the autonomic nervous system, let's see. Yeah, so the autonomic nervous system is split into the sympathetic and parasympathetic. Sympathetic is the fight or flight system, you know, get your body moving and you know, increase oxygen delivery to the tissue so you can be stronger and faster and stuff. And then there's the parasympathetic system, which is the rest and digest system. Like when there isn't a stress, calm your body down, store energy, digest food to get more energy out to your body, stuff like that. So this is kind of the broad stroke of your nervous system, your central nervous system in the center, and then peripheral nerves coming in and out of the central nervous system. Okay. Hang on one second. Sensor. I'm just checking my notes to make sure I don't miss anything. External hearing. Oh, pain reception. That's also external sensing. Nociceptive motor neurons, interneurons. So in addition to, you've got basically three different types of neurons. You've got your motor neurons that are coming from the spine out to your muscles and telling them to contract, or, you know, changing some of your physiology. So they're directly interacting with some organ and changing its function. And you've got sensory neurons, which you've got little sensors on them that receive information, send it back to your brain. Every other neuron in your body is an interneuron. So interneurons accept information from one neuron, process it. Remember, we talked about the soma adding up EPSPs and IPSPs, and then sends out information its axon in the form of action potentials. So interneurons are mostly what we're talking about. They're the most important thing for this class. Probably the simplest form of an interneuron is in a simple reflex. You can see this here in figure 4.2. You know, if you have, if your finger gets burned, you've got sensory neurons here in your finger that produce action potentials that come all the way into the dorsal root. And in the dorsal root, it'll then hit an interneuron, which is this guy here. And that interneuron will send information up to the brain, but also send it to this other interneuron here. And this interneuron then interacts with a motor neuron that causes muscle contraction. So this is a really short reflex loop that basically you feel pain in your fingers, you're pulling your arm back, yanking your arm back before the pain even hits your finger. I mean, before the pain even hits your brain. So you don't even know it hurts and you're already pulling your finger back. That's how fast that is. But then you also send that information up to the brain for processing to remind yourself not to do that anymore. Want to hear something messed up? This is what it was like growing up in the 70s. I had a friend, Hank, who his mother caught him playing with matches. So to teach him a lesson, she took him in the kitchen, she turned the flame on in the stove and stuck his finger in it to let him know what it would feel like if he got burned. That's the kind of people I come from. Okay. So, brain evolution. Where do the parts of the brain come from? Check my notes real quick. And it's funny, as kids, he told us about this and we thought, oh, yeah, well, that's what you get. You know, you shouldn't play with matches or get caught, one or the other.
More often.
There's a chat. Child abuse much? Well, back in the day, child abuse was on the menu. Okay.
Not to that extent, but.
Okay, so you can kind of separate the brain out into several different areas, it kind of on a broader scope. And they kind of mirror the evolution of the brain in that the most basic functions are way down in the brain here. This is the hindbrain. And by basic functions, I mean, that's what's going to keep you breathing, keep your heart rate going, keep you balanced while you're moving, all the really simple stuff that, and some simple reflexes here too. You know, I remember years ago, there's a big court battle over this woman who was, the doctor said was brain dead. And the parents would come and say her name and she'd turn her head and look. Well, there was no cortex activity going on. That was all just really simple reflexes down in here. So I don't know, different conversation maybe. So anyway, we call this our reptilian brain because we share this with all our reptilian ancestors, very simple parts of the brain. And then the more complicated parts of the brain are our mammalian brain, or the limbic system. The limbic system is about emotion and how emotions are used to control your behavior and direct you towards things that make you happy and away from things that make you sad. We'll talk a lot about that in chapter 5. So that's our limbic system, which is kind of a mammalian input. And then, I don't know, they separate into primate and human, but basically your cortex is all the most recent evolution. They call it the neocortex because it's the most complicated part and it's where the most complicated activities happen. Foresight and planning, long-term storage of memory, and memories in terms of muscle contractions to produce specific motion, and also memories like we think of, like narrative memories. And also there's a lot of sensory information gets processed first in these lobes of the cerebral cortex before it gets sent up to the frontal lobe where you're actually thinking. This is where the words in your head are happening, up here in the frontal lobes. Okay. That is our, and you can see in the next slide kind of how the brain has evolved over time. Here's a fish, right? Fish has got a whole lot of cerebellum, a lot of optic lobe, big medulla. So this is the simplest part of the brain, and that's about all fish have, okay? We'll talk about thalamus. It's kind of a switching area. But here's your cerebrum here, or his cerebrum, the fish's cerebrum, for Christ's sake, okay. But imagine this, all of this is that simple area of ours and at the hindbrain, right? So there's in terms of fish, they're basically sensing the environment and reacting to it very quickly. They're not thinking about anything. Here's a reptile, a little more complicated. Okay, we've got a bigger cerebrum, optic lobe, which is part of our cerebrum. Here's the cerebellum and medulla. So still we've got kind of a large amount of hindbrain compared to cerebrum here in the reptile, but more cerebrum than the fish. Here's a rodent. Now we're into mammalian, so we've got a large cerebrum, and it's bigger now than our hindbrain, so there's a lot going on here with this cerebrum. But you can see how smooth it is, okay? So a rat brain is, most of your thinking power is in the surface of the brain, so the rat has got a really smooth brain, not that much thinking power, but they do have a lot more foresight, planning, and like that than a reptile does. And here's the human with big fissured cortex. So this cortex is like overgrown. It's all over all the other structures. And there's a lot of big, deep fissures, which is increasing the surface area of the brain, giving you more thinking power. And you can see that even more so in this. Here is rat cortex versus human cortex. So remember, the white matter is tracks of axons going from one area to the brain to the other for communication in different parts of the brain. So here in the rat, you've got a thick layer of gray matter and then a thin layer of white matter, smooth surface, and that's all we got. Here, you can see how the gyrations in the cortex give a lot more surface area to it. And that surface area in the gray matter is where the cell bodies are. So your cell bodies are in the gray matter, and the white matter are tracks between different parts of the brain. So you can see between the rat and the human, there's a whole lot more gray matter, and that's where the thinking comes in. Okay, so medulla. So now we're going to go into the different parts of the brain. I don't know if I'm going to last until 4:15 because, again, I have a lot more fun in class. Oh, I know something I can do. Okay, never mind. Something to kill time. I mean to explain things better. So here is your hindbrain. Okay, again, compared to that fish where the hindbrain was like 3/4 of the whole brain, here your hindbrain is just a small part on the bottom. It's maybe a quarter, probably 20% of your brain. And the hindbrain is made up of 3 different things: the medulla, the pons, and the cerebellum. Now, medulla, we used to call it medulla oblongata, and I like that word better. But here's your medulla, and the pons kind of wraps around. It looks kind of like striated, and the medulla is more smooth. So pons, medulla. So the medulla is where a lot of the decisions get made about your housekeeping stuff, your blood pressure, your heart rate, digestion, all that stuff gets controlled by the medulla. So it's taking in the information from your sensory neurons, and some of that information will keep going up and go to the hypothalamus. We'll talk about that's involved in this process as well. But it's reflexively fixing things like your blood pressure. Like when you lay down, your body is at a level, and so when you stand up, suddenly your blood rushes down to your feet because it's water. Water just follows gravity, so it rushes down to your feet. Your medulla will kick in instantly and squeeze the arteries going to your legs, relax the ones to your head, keep blood going to your brain. You've probably all had that experience of jumping up quick and feeling lightheaded. Kind of feels like all the blood's rushing out of your brain. And that's because all the blood's rushing out of your brain. So the medulla can respond to that really quick and redistribute the blood to keep you going. And you can see why that would be like a reptilian or a fish level thing. I mean, every organism needs that just on a regular basis to keep operating. You know, you stand up and pass out, then the bear eats you. So it's a pretty simple function. Medulla, and in this medulla, you've got the area postrema. I talked about this in chapter 1. It's the chemical trigger zone, CTZ. Reduced blood-brain barrier, so toxins that get into your blood can get into your chemical trigger zone and cause you to vomit. So that's protecting you from eating toxins. And okay, so that's your medulla. Autonomic functions, housekeeping, just keeping your body going. Neurotransmitters that are really important here include GABA, gamma-aminobutyric acid. So we talked about this in chapter 3. It's a chloride channel activator, so it causes IPSPs. That's GABA. And endorphins, which are your endogenous opiates. So the opiates in your brain are really important here in your medulla. And so, you know, in drug overdose, oftentimes the reason why people overdose, especially with opiates, is overstimulation here of the endorphin receptors and depressing respiration. So respiration slows way down. And on top of that, you get vomiting, okay? So you're activating that chemical trigger zone. Your body's trying to throw up the toxin. And so you're not breathing much, you throw it up, and then you suck it back when you're trying to breathe and you choke on your vomit. That's called aspiration. A lot of people die that way, both with opiates and also alcohol. Alcohol does the same thing. So your GABA receptors here in the medulla are activated by alcohol, especially at high doses. It can be a respiratory depressant. Okay, so that is your medulla. Very, very important, especially for drug overdose. Pons is, you're not going to think about drugs interacting with the pons necessarily. It's basically coordinating movement from, you know, higher centers in the brain that are saying what to do and then sending that information down to your body and doing it, but also working with the cerebellum. So cerebellum's the next thing. Cerebellum is involved in making sure your body's in the right position for a specific movement. So think about this. You know, the first time you practice something athletic, you do it over and over and over. And after a while, you get better and better and better at it, right? So what's going on there is you're laying down memories in your cerebellum of, you know, what position should each of my body parts be in during this motion. And then when you repeat that motion, the information comes down to your pons, down to your body, and then sensory neurons in your body, proprioceptors, send information back up to the cerebellum to tell it where your body position is. And then your cerebellum does like air detection. Is everything right or is something wrong? And if something's wrong, it sends information into your pons and back down to your muscles to get you back in the right position. So cerebellum is really important for balance, motion, smooth motions. You know, if you don't have a cerebellum, you move really jerky because your body gets out of position. It has to be jerked back into position. And that includes, you know, your body as well as your mouth. And that's why, you know, when you get really drunk, you fall down a lot, right? Why? Because you get a little bit off kilter, and instead of your cerebellum saying, come on back up this way, straighten up, you don't get that cue. And so you keep going off kilter and off kilter and off kilter, and then you fall over. Or you catch yourself late and you jerk back up and you jerk this way and you jerk that way. So when you're drunk and your cerebellum is anesthetized, you don't have that internal proprioception that tells you where your body is. And also in terms of proprioception, one of the first things that cop does is say, stand up straight, put your head back, put your arm out to your side, close your eyes and touch your nose. So you've got no you've got no eye coordination with your hand. Your hand is just following its proprioception, which goes through the cerebellum. So if you're drunk, you can't find your nose. I know I got a nose. I came with a nose. Where the hell did my nose go? So that's one of the first things they do to see if you're drunk. Okay. All right, so cerebellum, learning new movements, integration of movement and posture, coordination of fluid movements, error checking between proprioceptors and memories, and it also produces muscle tone, which means it's keeping your muscles slightly contracted at all times. So, it kind of muscle tone. I don't know. See what I'm saying? I hear what you're saying. Okay, cerebellum. And the name means small brain because it looks like the cerebrum, but it's smaller and in the back. But there's no thinking that goes on here at all. There's a paper in your Moodle. Let's pull that up. We've got time to talk. So if you scan down into exam 2 area, I guess I don't have it here anymore. I used to have a reprint of a little article about a woman who was born without a cerebellum, and she seemed kind of weird. No one knew, I mean, she lived perfectly normally, except she couldn't really talk right, and she stumbled around a lot. So it's possible to live without a cerebellum. It's just not fun. Not fun. Okay. Cerebellum. So the pons is this tracks, coordinating tracks up and down. Cerebellum is helping for balance and stuff. And down here in the medulla, it's all about housekeeping. But embedded within this structure, not the cerebellum, but between the medulla and the pons, there are a number of just strips of cells that work together. Let's just move on, and we will talk about it. There are 3 different. Hang on a second. Okay, sorry about that. There are 3 different tracks here that we're really, really interested in. They start here in the raphe nucleus, and they go up to the rest of the brain. Bless me. God knows I need it. Okay. So 3 different areas. One is the raphe nucleus, and this is really important. Make sure you know this, because later we're going to get into drugs. I'm going to be talking about these 3 pathways because they're very specific to neurotransmitters, which means they're going to be specific to certain drugs. So your raphe nucleus is down here in the medulla, sends axons up to the whole rest of the brain. Your RAS, reticular activating system, is also here and sends axons up. And the third one, which I don't have here just because it was already complicated enough, is the ventral tegmental area. And that also comes up, but it only stimulates the limbic system. So you've got these 3 different tracks. You can't see my hand over here. Oh, I got to put it in front of my face. You got 3 different tracks. Your raphe nucleus. In the raphe nucleus, the neurons' bodies are down in the medulla, but the axon bulbs are at the other end, and the axon bulbs all release serotonin. So this raphe nucleus is putting serotonin out all into the brain, and this is a mood stabilizer. Basically, it keeps you happy. Not joyful happy, whatever, but just kind of like relaxed and happy. Serotonin. So when you're kind of upset, you're in a low serotonin situation. When you're just kind of stable, relaxed, and happy, that's a high serotonin system. So raphe nucleus is going to be involved in mood stabilization, basically. Your reticular activating system is involved in waking up, and not just waking up in the morning, but being excited and stimulated versus relaxed and calm. So this is norepinephrine. Norepinephrine is all about being active and we just got a chat. What's the difference between dopamine and serotonin? Okay, I didn't get to dopamine yet. I'll get to there in a second, and then you'll see the difference, I hope. But we'll talk more about it in the next chapter. So Reticular activating system is norepinephrine. It's stimulation. You know, when you say you hear a loud noise and you turn, you get excited. You know, that's norepinephrine. But it's more than that, though. You know, if this system was gone, you wouldn't wake up. You just be in a coma. But also, so it's got that effect of waking you up. But also, you know, when you feel like high energy and you're really, really motivated, that's norepinephrine. And when it goes away, then you're a lot more relaxed and calm. And then the third system is the VTA, and the VTA then stimulates only the limbic system, and that's all involved with joy, not happiness so much as joy, oh God, how do you describe this? It's like the difference between dopamine and serotonin is the orgasm, and serotonin is the relaxed, happy feeling after the orgasm. That's the best way to explain it. So, you know, it doesn't have to be orgasm, though. I mean, when you eat a good meal, eat something good, it tastes good, it makes you happy. That's dopamine. But after you've finished eating and you just, oh, belly full, you got that feeling, that's serotonin. So it's kind of like the difference between sex and love, you know? I mean, sex is really exciting and stuff, but love is a deeper thing and it lasts longer. So Julia, did I answer that question? I'm hoping. Julia Waters. Yes. Okay. And we'll talk more about that again in the next chapter. But anyway, keep it in mind, these three systems, because they are norepinephrine, dopamine, and serotonin, and they're going to be affected by a lot of the drugs we talk about in the third section of this class, because they can be related to addiction. Okay, and serotonin's more in the hallucinogen chapter, frankly. Midbrain. Okay, so midbrain here, honestly, not that important for this class. Basically, it's similar to the pons, where it's bringing information from the movement centers higher in the brain and bringing it down into the lower parts to be kind of processed by the pons and the cerebellum, and then sends it back down. So not that important, Mr. Midbrain. So we're not going to worry about it too much. But, oh, wait, we missed something. Okay, this guy, thalamus. The thalamus is very important. So basically, any information coming into your brain, I think except auditory, I could be wrong about that. Or maybe anything except olfactory, your sense of smell. Any information coming into your brain goes through the thalamus first. And the thalamus is kind of like a filtering and switching center. So it filters out the nonsense, the things you don't really need to focus on, and kind of emphasizes things that are important. And so so it's going to do that, but it's also sending the information where it needs to go. So for instance, light comes in your eye, right? Retina hits the retina makes it into action potentials. They come back to the thalamus, and the thalamus then sends it back to your occipital lobe. But before it sends it back to your occipital lobe, it decides how much of this is important. Do you really need to focus on this? Or is this just extraneous information that's going to confuse you? So that's kind of what the thalamus is doing there. It's a really important filtering thing, as well as a central switching area where everything comes into it and it sends it off where it needs to go, if it does need to go off. Otherwise, a lot of things go there to die. Okay, and so underneath the thalamus is the hypothalamus. Hypo meaning under, thalamus being thalamus. And they don't really operate together that directly. I think it was just named anatomically. And below the hypothalamus is the pituitary, which is the master gland. So we'll talk about that in a second, but let's do hypothalamus first. So I said that the medulla is involved in all the housekeeping aspects of your body, and that's kind of like on the low level housekeeping stuff. So nothing complicated, just really low level, keeping your heart going, keeping your blood pressure going. Thalamus, though, is involved in some more complicated things. The basic 4 F's, I love this, plays a major role in the regulation of basic biological drives related to survival, including the 4 F's: fighting, fleeing, feeding, and mating. Badumch. This is actually in a textbook somewhere, which I think is hilarious. Okay, so anyway, it's kind of more complicated reflexes, when is it time to fight and when is it time to run away? And fight or flight, that's your sympathetic nervous system. So your hypothalamus is going to tell your medulla to kick in the sympathetic nervous system, get more oxygen to your muscles, more glucose to your muscles, get ready to fight and whatever. Feed is going to tell you when you're hungry, your hypothalamus. When we get into the, surprisingly, the cannabis section, we'll talk about how your hypothalamus is important in directing your hunger, whether you're hungry or not, and how cannabis affects that, or you really do get the munchies. So I've heard. And also mating, what are your mating drives? Where does that come from? Why do you feel horny one day and not the next? That's your hypothalamus controlling that. So again, it's automatic stuff at a higher level than what the medulla works on. Hypothalamus, lose interest in eating. So eating, important. Animals must be fed intravenously or they starve. Okay, let's not starve the cute little animals. Where are we now? Raphe nucleus, VTA. Medial forebrain bundle. I guess I should have said that earlier because it'll come into play later. But I talked about the three different areas, the Raphe nucleus, the VTA, and the RAS. They are all pretty close together. And when their axons come out, they come together into one big bundle of axons called the medial forebrain bundle. So they're all together, and they go from the medial part of the brain to the fore part of the brain, medial forebrain bundle. That'll be important later when we get into chapter 5, so it's good to know about that. Okay, another part of the midbrain that I didn't talk about is the substantia nigra. So, I'm trying to remember now. I think the substantia nigra is next to it's like the dorsal tegmental area or something. It's right next to the ventral tegmental area. And there are neurons there that use dopamine that are really important for movement, stopping movement, basically. And these are the neurons that get broken down when someone's got Parkinson's. That's why their hands keep shaking, because they can't control their movement anymore. Because the substantia nigra sends axons up to the basal ganglia to inhibit it. Otherwise, the basal ganglia just randomly sends information down. Your hands shake, your head shakes. It's really, really bad. And also here in the midbrain is the para-aqueductal gray matter. It's not a great word. I tell you what, you learn this word and go home and tell your mom, you will blow her mind. But it's actually, with all these words, all the good words anyway, in my opinion, when you take them apart, you can see what they are just by the parts of the word. So peri-aqueductal, peri means around. So this is around the aqueduct. So you've got this fluid part of your brain. It's almost like blood running through your brain, but cerebrospinal fluid that flushes up through the brain and then comes back out into your circulation, I believe, and it clears out a lot of junk. So that's the aqueducts in your brain. You've got ventricles that are open, fluid-filled spaces. So these neurons are around the aqueducts, and gray matter because they're cell bodies. They're gray. So para-aqueductal gray matter, there in your midbrain. And this is important because you've got endorphins there. And when pain comes up through your spinal cord to your brain, it goes through the PAG. And if you've got some opiates there, some endorphins going on, it'll block the pain. So you don't feel the pain. And this is why, if you're in danger and you cut yourself, it usually doesn't hurt. Usually it doesn't hurt all that much and you're able to keep moving and get out of the danger situation. And then when you sit down and relax, then it starts to hurt because pain reception is controlled in the brain in this area. So, just probably evolutionarily, it's better to be able to get out of that situation without worrying about the pain. And then later you feel the pain to know that you're hurt and you have to do something about it. So anyway, bottom line, midbrain, the two things I forgot to talk about, substantia nigra, which we probably won't talk about much in this class, but that's the area where when the cells die, you get Parkinson's. And then the para-aqueductal gray matter, which we will talk about in chapter 8, I believe. And that's where you've got endorphin receptors involved in pain reception, blocking pain reception. Thalamus, central switching area. I believe I talked about, I'm just looking at my notes now. I believe I talked about all this. Oh, so one of the examples I like to use, and it comes into play in chapter 6, is, you've probably all done this. You're driving down the road and you look and you go, oh, wow, I'm already in Cortland. It's like you're not paying attention to all the other things going by. You're thinking about the music, you're thinking about what you're doing, where you're going. And, all this visual information came into your brain, but you didn't even notice it because your thalamus is just filtering it out. It's not important. So that's part of your thalamus activities is filtering that out. Hypothalamus, regulation of physiology, homeostasis. Oh, the hypothalamus also regulates the pituitary gland. So I talked about the pituitary gland briefly there. I said, it's the master gland in the body. So basically what happens is, they call this the HPA axis, where the hypothalamus stimulates the pituitary gland, and the pituitary gland releases a releasing hormone. And that goes into your bloodstream and goes out to some endocrine organ like your adrenal cortex. And then that releasing hormone will cause the release of other hormones, adrenal cortex hormones, cortisol, things like that. And then that goes off and has an effect. So your hypothalamus is controlling hormonal influences in your body by controlling this the hypothalamus goes through the pituitary, and then the pituitary controls your endocrine gland, and then your endocrine hormones control your body. So that's how that works. And also the hypothalamus controls your autonomic nervous system. So it's controlling the medulla from above. And it's regulating things like thirst, hunger, sex drive and fertility, emotion, water balance, lactation. Now, when I say emotion, it's not directly causing or creating your emotion, but giving you the response to emotion. So we'll talk about the limbic system. Your amygdala is involved in deciding on emotions, and it sends information to the hypothalamus, and the hypothalamus then sends information down your spinal cord and makes your body react to that emotion. So, like you see someone you find really attractive and your stomach gets all fluttery, that's your amygdala said, woo, and your hypothalamus says, I'm on it, and it sends the information down, and then your stomach gets fluttery. And if we were in the state of nature, you would probably end up having children. But we've got a cerebral cortex, we can control that kind of thing. Can't we, people? Yes, we can. Okay. So it produces, basically what I'm saying is it produces the internal feelings that are based on inner emotional state. So when you feel different emotions, your body feels them, you can feel it out in your body. And that's the hypothalamus sending information out to your body to produce that feeling. And it can be kind of like a circular thing where your amygdala decides you should be scared and sends scary signals down to your body gets scared, and the scaredness of your body comes back up to your brain and tells your amygdala, hey, I'm scared. And your amygdala says, you're scared? Oh, well, let's be scared. And it can be a bad circuit sometimes. It can get out of control. But that's not what we're talking about now. Okay. Limbic system, Mr. Limbic system. So we're going to talk a lot about this in chapter 5. Oh, basal ganglia. Basal ganglia is involved in movement. Okay. Limbic system. So the limbic system is involved in emotion, and you've got 5 areas that are really important. Really 4 in this middle of the brain part, but 5 altogether. So you've got your dorsal striatum, nucleus accumbens, the amygdala, and the hippocampus. And then the 5th area is your cerebral cortex, prefrontal cerebral cortex. And so this is all involved in behavioral modification. So dorsal striatum's where habit-like memories get stored, habits. Nucleus accumbens is your reward system. When you do something good, you feel joyful about it. Oh, I feel really good. I got an A on the test. That's your nucleus accumbens. Oops. Oh, shoot. Amygdala, like I was talking about before, is involved in emotions. So sensing your external information and deciding on what kind of emotions we should have based on this. Mostly our emotions are bland, like nothing going on, but then something happens and you change and that activates your emotions and that comes through the amygdala. Notice this bad boy too, your olfactory bulb comes in right to the amygdala. And that's why smells can give you a really strong emotional experience. I got to tell you this. This is from a long time ago, but senior year in college, I had a bit of a crush on this one woman. I wouldn't call it a crush. We were involved with each other, and she had this particular perfume she would wear. I still smell it someday, and it takes me like 40 years back all of a sudden. Olfactory memories are really strong in terms of your emotions. What are the 5 parts of the limbic system? The dorsal striatum, nucleus accumbens, amygdala, hippocampus, and the cerebral cortex. And we'll go over that in a lot of detail in the next chapter, so don't worry too much about it now. Let's see. I'm just checking my notes to make sure I didn't forget something here. And the nucleus accumbens is the key, really. Things that stimulate your nucleus accumbens are very addicting. So basically, you've got the combination of reward, emotion, habit, planning, and memory. So it's, you know, how do you learn based on your experiences? It's your amygdala, it's your limbic system. So drugs that affect this: cocaine, amphetamines, ecstasy, THC. These are all your addictive drugs. Less so ecstasy, but less so THC, but they're all addictive. And also indirectly affected by opioids, like morphine or heroin or fentanyl, and alcohol. Alcohol also indirectly causes the release of opiates, which then stimulate your reward system. And that's why alcohol can be addictive too. Okay. What is it? 417. Thursday. Okay, here's the deal, people. I'm going to stop share. Let me see your faces real quick. Ooh, Matt Cole, take your face down. Yuck. No, I'm just kidding. Teasing. Sorry. I can't help it. Just who I am. Okay, so here's the deal, people. We can go ahead and finish this chapter today and take Thursday off. I always do like one chapter a week, so I don't want to get too far ahead. So let's see a show of hands. How many people want to finish the chapter today, and how many people want to finish it on Thursday? How many today?
Finish.
Wednesday.
Oh, Wednesday, sorry, Wednesday. Anybody want to do Wednesday? How many people want to do Wednesday? 1, 2, 3, 4. What's that?
Let's finish it today.
Finish it today.
Yeah.
2.
Oh, let's see. I think there's a way to do this. Polls. Ooh, we can do a poll. Add a question. Hello. Oh, not. I don't know if this is going to work. All right. I don't think I can do this on the fly. It just took me to a different website.
Do it on the chat.
Chat. Okay. Okay. People chat. Yes to finish today. No to finish Wednesday. The yeses are pretty strong. Looks like a yes. All right, let's go ahead and finish it today. It'll probably take me another half hour. And then Wednesday we can get the afternoon off. Okay? Rock and roll, people. Rock and roll. All right. To the cerebral cortex. So another thing here that I didn't mention, but is an important part of it, is right here, this cingulate cortex. So the cingulate cortex is between your limbic system and your cerebral cortex. And your cerebral cortex is the thinking part, and your limbic system is the emotional part. So this is kind of the transition zone between one and the other. And it'll be really important in chapter 6. We'll see that the cingulate cortex is kind of cut in half. You've got the anterior cingulate cortex and the posterior cingulate cortex. Excuse me. And each of them will have a different role involved in brain function. So keep your cortex in mind, your cingulate cortex in mind. Really important. Okay, but let's go to Mr. Cortex. So the cortex now is the biggest part of your brain. It covers your all the other parts. It's the most advanced part of the brain, and the outermost layers of it are the actual cells and the cerebrum. So you've got 6 layers of cells in gray matter, and that's where all the cell bodies are. So that's where all the calculations are going on. So like at the end of chapter 3, we said, the cell body's taking in all the inputs and making decisions. This is where that's happening here in that gray matter, the outer 6 layers of your brain. And you've got these deep fissures. I think the outside parts are gyri and the inside are fissures. So this increases that surface area. So that's really important to get you more gray matter. And your cortex is split into 4 different lobes. You've got your occipital lobe here in the back, and occipital lobe receives and processes visual stimulation, which is kind of ironic when you think about it. Ironic? Counterintuitive anyway, because your eyes are up front, and that information from your eyes has to go all the way to the back of your brain, well, through the thalamus and then to the back of your brain to get processed. But that's where it happens, back here in the occipital lobe. And that's why when somebody smacks you in the back of the head, you see stars. I just made that up, but it may be true. I don't know. Christy would know more about that. When you've got an active patient and you want to quiet them down, you give them a good smack in the back of the head, right? Isn't that the way it works as an EMT? No, that's old school. Yeah, you don't do that anymore. Okay, fair enough. So that is your occipital lobe. Then you've got your temporal lobe over here, and the temporal lobe is right over your ears, which is a good place for it to be because that's where your hearing comes in, your temporal lobe. So this is processing hearing. And then you've got your parietal lobe. Parietal is really important for us and in general. So your parietal lobe, number 1, is bringing in sensory information. So all that, physical, tactile, sensory information comes into the parietal lobe. And there are specific parts of the parietal lobe that are dedicated to specific parts of your brain. There's some really cool pictures I've seen. I don't think I have one here, where they take your parietal lobe and they put the part of the body on it. And you can see how it just lines up with your body. And different parts of the body have larger sections, like your face has got and your mouth has a really large section of the parietal lobe, because a lot of sensory information comes in there. And then other things like your knees and your feet have small areas here. But anyway, sensory information comes in your parietal lobe. But also, long-term storage of memory is here in the parietal lobe. So lateral parietal lobe and the other parts of the parietal lobe are involved in long-term storage of memories. And we'll talk about that a lot in chapter 6. So that's your parietal lobe. And then here's your frontal cortex. And frontal cortex is pretty big. Most of it, I would say, if I cut a line across here, well, hang on a second. Wait a bit. Let's see, there, okay. So cut a line across here. This part of your parietal lobe is stored memories of how to move your body. So when you raise your arm, you've got dozens of muscles that have to contract in the right order and at the right strength to give you that perfect movement. And which muscles to contract in what order and all of that special information is stored here in your motor cortex. Well, anyway, let's go to the prefrontal. So the prefrontal then is your thinking part. That's where your thoughts are and where you do all the computational things to do what you do every day. The very front of it here, medial prefrontal cortex, orbital cortex they call it sometimes because it's right behind your eyes. That's kind of your relaxed, mellow thinking part of your brain. We'll talk about that in chapter 6. And then your dorsolateral prefrontal cortex up here, that's the more focused part of your brain when you're on task and you're performing something, is out here. But in general, your prefrontal cortex then is what you think about when you think of your brain. What do you think about? Oh, Einstein, he had a big brain. Well, it was this part of his brain that he was using for all of that that cognition stuff. So cognition happens here in your prefrontal cortex. So to get back to your motor cortex, your prefrontal cortex, probably dorsal medial, would say, let's move this arm and move it really quickly. And that information would go to your motor cortex. Your motor cortex would find the combination of muscle contractions that it needs to do that thing, sends it down to the thalamus. The thalamus then sends it on to the midbrain. Midbrain sends it down to the pons, and the pons then sends it down your spinal cord and out to your muscles. And your cerebellum is making sure you're doing it properly. Okay, so that's your motor cortex. Okay. So your frontal lobe then is deciding on voluntary movement, and also forethought and planning, all your executive functions. You've got 3 layers of cortex in each part of your brain. It's easiest if you think about it in terms of your sensory parts of your cortex. You've got primary cortex, where it directly receives that information from your thalamus, receives the sensory information from your thalamus and kind of recognizes it. And then your secondary cortex kind of makes an awareness of it, kind of makes a story out of it, makes a picture out of the primary cortex stimulation, makes a picture out of that so you can understand it. Your tertiary cortex then will associate it with other parts of the brain. So you're looking at something like a flower, and it's going to associate that with the smell and the temperature of the day and everything else, and put that into one big story, send all of that through the thalamus and then back up to your prefrontal cortex, and that's how you're sensing the world. So each of your cortical lobes has got layers, and there's the simplest layer, more complicated layer, and then the associative layer that associates what you're doing with everything else. And we'll talk about this when we get into hallucinogens, how hallucinogens like LSD will directly stimulate this. So, you're getting primary cortex stimulation without having any visual stuff coming in through your brain. And that's what your hallucinations are. Okay, you've got this stimulated cortex, and your secondary cortex says, oh, we've got the stimulation. What do we do with it? Let's make some cool patterns with that. And then you see geometric patterns and weird stuff because that's what your brain's doing with it. Okay. So in general, the cortex is involved in higher order perceptual functions needed for purposeful action, rationality, thinking, behavior. Okay, oh God. I think I picked up a virus because I keep getting these alerts to get some virus protection. Okay, neurotransmitters here, acetylcholine is really important. We'll talk about that again when we get into hallucinogens. Anandamide, which is your endocannabinoid, THC receptors, and serotonin, psychedelics. That serotonin is coming from your raphe nucleus. And serotonins will muck that up. The psychedelics will muck that up and give you some really interesting experiences. Okay, and unfortunately, that's about all I have for this week. Holy cow. Jesus, Dr. Slush. They're paying you for this? I guess so. I guess so. Is that all I have? Hang on. Don't go anywhere. Oh, that is it. That's the last slide. So this chapter, I would say definitely read it. It's definitely worth a read. I've just kind of skimmed the surface of it to give you the highlights. But hopefully you've bought the book or borrowed the book or stolen the book. I don't care. Make sure you read that book. And that's about all I have for this week. Let me stop share and see your faces again. Say hello, everybody.
Hi.
Sean Reeser, the man.
Hi, thank you.
Esha Gupta. Hi, Esha. Kaya Lofton. I don't think we've met before. Hello, Kaya.
Hi, Dr. Slush.
Okay. Saksham, everything okay with the test last Friday?
Yes.
Yes, okay, good. All right. Any questions or comments? So we'll skip Wednesday afternoon, right? And I'll probably still be sleeping by 3:30 Friday afternoon. Just kidding.
Same.
I know you will be. Yeah. All right. Well, let's call it a day. Oh, wait, 5 new messages. Let's make sure everything's okay. Yes, everything's okay. All right. Well, all right, guys. Well, have a great day and read the textbook. Talk to you later.